Thank you, everybody. This is Debabrata Ghoshal. I am the organizer of Washington Quantum Computing Meetup, DC. You see the today's presentation with Dr. Wojciech Burkot. We are honored to have him here today. He's the co-founder and chief physics officer at Beit. You read his bio, and so he'll enlighten us about a seminal result on unstructured search algorithm by Grover. Now, our program is sponsored by CQC and Association Quantum. We have to talk about some Association Quantum little bit more because they are our new partner. Association Quantum, a non-profit organization which is dedicated to spreading quantum knowledge. They have a lot of exciting webinar coming up, so please check their website for more details. They are also supporting other meetup groups with webinars. So if you need any help, please feel free to contact them. Okay, and I have a couple of announcements that coming up. The next one is the history of quantum with Dr. Shalil Betkihal. This is the Association Quantum, and you can see the website there. You can check it out. That is on May 27th, 11:30 to 12:30. And the next one is ours, which is done by Dr. Cyril France, professor at Harrisburg University. We will talk about the foundations of quantum computing, complex numbers. This is like a tutorial kind of webinar, so please join that. And also on 9th of June, we'll have a tour through the quantum ecosystem by Doug Pinke, managing editor of Quantum Computing Report. Try to look at the website, our website, Washington DC Meetup Group, and you can find the details. Okay, thank you. So I'm going to, get it to Dr. Burkot for the next presentation. Thank you.
Thank you very much. I hope you'll be able to see and hear me.
Yes, I can see.
Bring your shared window to front. Okay. All right. Do you see that now, the first page?
Yes.
Okay. So I'm Wojciech Burkot. I'm a recurring physicist, and actually I did change the title of this presentation as it was announced for the following reason. The title, as originally stated, was just a part of the first statement. I'm not arrogant enough to claim that we actually have a seminal result beating Grover search. However, we are really involved in trying to find this. Let's have in mind that so far, nobody on the actual hardware was able to show the actual operation of the Grover search algorithm on the hardware. There was an attempt back in 2018, and all which can be shown was finding one element out of 8 after very many trials and with a significant error. Finding one element out of 16 have proven to be out of the capabilities of the quantum computing hardware. we at Beit started working on trying to help with the solution for the real world problems. We started with really hard problems for warehousing. However, it turned out that our classical solutions were better than what we could achieve with the actual quantum hardware, which led us into pivoting, into finding a better ways of expressing our algorithms and implementing them, taking into account the limitations of the current existing NISQ hardware. So for that, I want to share with you our work, and the plan of this presentation is going very shortly through the base, then making fun of myself essentially. I'll show you something, how it started. Then we'll talk about focusing on the structure of the problem. Everybody knows that the GROVER search is dealing with unstructured data, and we'll address this shortly. Then I'll mention some tools, jump to the solutions, and then discuss the work in progress at Beit. However, we are not ready yet to talk about the multi-target oracle, and we are not going to disclose the results on the hardware runs. Those were slowed by the pandemic, so while we can work remotely, our hardware partners are significantly slowed by the pandemic. So for them, it's much, much harder than for us. Also, we do not going to, or I'm not going to talk about the application of the solutions we present to hard problems just yet. I think we'll be ready sometime in the future. It is not now, so it's out of scope for this presentation. The physics as we know it is essentially continuous down to the quantum level. So the quantum computers take certain approximations to be able, following the idea by Feynman that if there is a way of breaking Church-Turing thesis, it would be via quantum. And for that, for being able to build hardware which is not fully interconnected to the point that you cannot really do anything useful because modifying the dynamics will be so hard, there are certain techniques which were used, known for many years in physics for studying, say, quantum systems. However, they were crucial for for creation, even theoretically, of quantum computers. Essentially, we split time into the very short moments, and we assume that the evolution of the quantum state within those moments is under the operation of unitary operators, which can be derived to mimic what is stemming from the Hamiltonian of the system. The other big assumption is, that was time. The other big assumption is space, Hilbert space actually, if we go into that level of details. And the problem there is that you cannot really talk across this space freely. So essentially any hardware realization needs to take into account only local interactions, meaning 1 and 2 qubit gates, if you approximate them with the unitary operations. So with that said, I will never again return to this. Just have in mind that any box you'll see on the wires representing qubits are unitary operators. I'll be describing how we use them and for what purpose. People often say that the writing algorithms for quantum computers is about as hard as finding a solution to the Rubiks cube puzzle. And there is some truth in saying this, just because if you try to focus on the particular state, your target state you want to amplify, the rest of your Rubik cube is actually modifying as well. However, I would just draw this analogy a little bit further, in a sense that when you are playing with the Rubik puzzle, at least you can see the colors. However, when you are playing with quantum systems, any measurement, especially the measurement which you will need to see the whole face or whole cube, collapses the system and gets into something which is just equivalent to running this whole thing on the classical machine. You can see the part of the Excel sheet there with colors, not really matching the Rubik cubes. However, that was instrumental in us getting to the solution which we'll be talking today. Essentially, regardless, if you plan your operations carefully, regardless of initial lack of the structure and initial inability to tag the particular element with the oracle, I'll get into the details how it is done in the classical, sorry for the word classical here, in Grover search. Then you might be able to notice that there are certain patterns which essentially create the structure which can be used by the computation. And you can see some numbers in, and that's actually the amplitude in the systems. We wanted to concentrate the amplitude in the green, signal green colored cell in that spreadsheet. So the basics, we talked about the local interactions. However, if you go into the details of the Grover algorithm, you'll see that because it is unstructured, the operators you use in the obvious description of the algorithm need to span the whole space. And that's, you'll see on the left, first the essentially Hammarad transforms applied to all the input qubits and some ancilla qubits, which are used later on the right-hand side. So there is an equal superposition of all 16 states, not taking into account the ancilla ones. So you'll see just the boxes with the amplitudes and phase. The size of the bubble inside is proportional to the amplitude. The direction of the small dash there is the phase. You'll see that we start with the equal superposition, and then we do the CCC0, which moves a single element to the space of its own because the first ancilla qubit is now set to 1, and everything else stays in place. How to convert that to the more usual multiple controlled Z gate is pretty obvious trick, and that's something which you'll be using daily playing with the quantum circuits. However, if you try to implement that, there is a beautiful decomposition. However, it has a pretty nasty feature, namely, if you add qubits, such an operator will require the number of 2-qubit gates on the acting on the newly added wire to be twice the number of the 2-qubit gates of the system of the highest number of those gates touching the qubit in the system smaller by 1 qubit. So that's the reason why it is so hard to run the Grover search on the existing hardware. We need to remember that the gate or circuit depth for those hardware implementations is in the low tens. So imagine, and well, the people are now preferring to count that in the number of sequential 2-qubit gates, it's a closer measure to the complexity. So another solution, rather than expanding that exponentially, is to use ancilla qubits. Well, it's cheating only a bit, because adding any ancilla qubit essentially increases the space, Hilbert space you are talking about, twofold. So the circuit to the right does exactly this. There's also non-construction. All we need to use is so-called Toffoli gate, and multiple times. And each of those Toffoli gates, CC0, can be decomposed exactly by using 6 C0 local gates acting just on the pair of qubits. However, you can see how many of those you need, even if you use ancilla qubits. It's cheaper. Nevertheless, it's still extremely expensive. Executing just a single CC0 here will take 6 times 7, which is out of scope of most of the existing hardware implementations. How can we, before we go into trying to overcome, let's think what stays in the way of the efficient computation, the Rubik cube solution. It should be mentioned as the last. I screwed up my slides, so it's first. The Grover search is provably optimal, and that's what I referred to as the seminal result. You cannot do any better than use pi/4 times square root of the number of the elements you are searching from. And that's a mathematical fact. So you cannot go better than this, which seriously limits what you can do in real life. It can be only worse, right? Because of the decoherence, because of the gate infidelities, and so on and so forth. The other challenge is related to deferred measurement principle. Essentially, there was a concept that you can try to overcome the difficulties in running long circuits by taking in-circuit measurements and then executing the remaining part of your circuit depending on the measurement result. However, the deferred measurement principle, which is taken from textbook, right? This is something which we teach students, says it doesn't matter. If you can defer all the measurements to the very end of your computation, probabilities will remain the same. However, I'll ask you to pay close attention to the assumptions and to the thesis of this theorem. The probabilities will be exactly the same. It doesn't say a thing about the circuit complexity to get there. So we'll be revisiting that one. And yet another one, I particularly like this one in the formulation of Wojciech Burkot, the great Polish-American physicist, not only because he's my namesake, but also because he's my compatriot. He's originally from Krakow and spent a lot of time in Los Alamos. Essentially, this means, why is it important for quantum computing? Essentially, Nocloning Theorem excludes the possibility of running a tree-structured computation. When you do the copy of your state, you do your computation with one of the copies. If it fails at the measurement, you just return to the copy you've just created, create a copy of that, use one of the copy to run your computation, till the measurement, and so on and so forth, right? This increases the probability of success. And we cannot do this because of the no-cloning theorem. And again, this is important to understand what that means. You cannot get two identical state, well, the copy of the unknown state as a tensor product attached to in the space adjacent to where your state is. There is nothing wrong with actually making the copy which is still entangled with the original. That can be done, that's easy, that's calculating the function which is identity, and we know that you can calculate any function, even irreversible function on any quantum state. So that would be easy. However, it doesn't help, because once you destroy part of that via measurement, for example, at the end of your computation, you destroy the part which is entangled with it, and you are not getting your copy. So essentially, the proof is simple. It's just against the unitarity. You cannot do this because you are bound by the unitary evolution. So those three things make the finding a better solution to the unstructured search problem hard. It is hard, and it takes a really long time, and you'll see that in a second, to wrap your head around the problem and try to get something which resembles the solution. So here is how it all started. This is a bit of the history of Beit. You can find that on arXiv, but please don't, just because it is completely wrong on so many levels that I'm really ashamed. However, it was created back in 1997, so not many people worked in that area, and my stupidity should be excused on just this. This was early beginnings. However, that idea stuck in my mind, and thanks to my co-founder, Wojciech Burkot, he is a mathematician, so he was able to straighten me up, and I'm not talking those things anymore. So still, it took a long time. Let's try to run it. Just brute force through the whole problem. We are really good. If you don't know, you might not know, the three of Beit engineers slacked at work and went to participate in IBM Quantum Challenge. And it was the random sample of the Beit engineers. And they got second and third best results globally, among very few people who are actually able to complete the challenge number 4. And we are extending the offer, employment offer, to anybody who was in that area or better. We do run pretty robust recruiting process. I can say this as the next Google engineering director: getting to Beit is harder than getting to Google. And we want to keep it that way. So why don't we try to brute force? We prepared a circuit which does some clever stuff around partitioning the Grover search algorithm into parts which are manageable, and in such a way that we can continue with the independent circuit. And as you can see, the first circuit, this is the output from Qiskit, the IBM tool which enables running the quantum circuits on simulators and on the actual hardware. The circuit has entered. You see that there are some limitations. I don't know if you know, this is worth noting that the C0 on IBM Q is directional. So in order to do the C node in the direction you wanted and not the one hardware wanted, you need to use the identities and convert that to the other directions using Hadamard operators. Qiskit does have an optimizer. You see the output of the optimizer in the second row. We did better. We have an internal tool which makes circuits even shorter. However, even that short circuit didn't run properly. It runs beautifully on the simulator. It gets you the marked element as you wanted, except that it doesn't run on the hardware, because when it's transpiled into actual microwave pulses controlling the superconducting qubits of IBM Q machine, it gets much longer and it cannot really be completed. So the result from 2018, if you run it yourself, you will see where the problem is. We are getting the circuit, which is like 1/8 of the original circuit run in 2018. Nevertheless, it is still too long, and I don't believe it can be optimized anymore, unless you start doing tricks. And the rest of this presentation will be about tricks in quantum computing. So as you can see by the picture of the amplitudes where my cursor now is, we are not trying to find a single element. We are satisfied with running the computation in such a way that we know just 2 qubits of the result, and we can restart with the independent circuit, setting up those qubits as they were measured. It's very short circuit, and if you go to that part, you might be able to recognize something which is not really a CC NOT gate. It is an approximation closely resembling closely resembling the Norman-Margulis approach to the CC NOT gate. And here, please allow the personal plug. I got the quantum computing bug in 1993 at MIT, coming from behind the Iron Curtain from the communist country, invited by those guys. I had the pleasure of working with Professor Thomas Toffoli and Professor Norman Margulis at LCS at MIT at that time. So after all those many years, their contribution to the field is still being used. Back to the Margulis gate. Oh, this is not exactly Margulis gate. It's something resembling the Margulis gate in structure. It's almost good, almost CC naught, except that it does change the phase of one of the output states. However, if you run all your computation in such a way that you are interested in just 4 states, not a single one, it doesn't really hurt. And you will see another one of this over here. You see swap here. We are trying to match this to the IBM Q topology. And neither this nor other attempts, well, you see this is pretty elongated. That was the attempt where we knew which qubit and which qubit pair is the best, having the best fidelities if you operate on them. And we tried to match the qubit to the quality of the particular qubit, to match the circuit to the quality of the particular qubits. That's the result. Then we went completely different way and tried to balance the number of the gates executed on every single qubit. And guess what? It didn't help either. So I'll get to the theory behind that slightly later. But the previous circuit already used those techniques which are explicitly mentioned here. See what happens. This is almost complete CCC-Z, except for 1, 2, 3, 4, 5, 6 qubits and one ancilla. Except that it's split by the technique which I mentioned before. You are using ancilla. You should be uncomputing that part over here. But look what happens. If your diffuser, if your diffusion operator is not spanning the full space here, then you will be uncomputing that part by exactly same operator here, but then you'll be computing that again. And those operators actually are self-inverse, and they cancel out to just identity if there's no intervening operation on those qubits. And you see that used here and here, and only here. I think I see the error. It doesn't matter much because those two do commute, but this operator should be outside, because the uncomputing of this whole block of control Z's should be happening somewhere here. Luckily, those two commute, so the order doesn't matter that much. It should be outside for the proper description. It should be outside of the of all those oracle operators here. So that's one of the techniques we are using. And yes, it is here on the pretty small circuit. Nevertheless, we know how to use this, so it can be beneficial, reducing the circuit depth by not uncomputing unnecessarily. So that's one of the tricks we are using. We did patent parts of this, and I'll get to that why we are not so much into the open source in that world, but more towards the end of this presentation. So just please note one technique: don't do unnecessary compute uncompute if you are using ancillas. That shortens your circuit depths, and that's something which you can use. The only thing from that slide is just remember this: you don't have to uncompute here. However, if you are touching those qubits, like this diffusion here, you need to uncompute, and it's happening here. And since you are using this, you need to uncompute also this one and compute that again. That one can be spared because that's the last one in that circuit, meaning you don't care whether you really screwed up your ancilla bits, nothing happens to them anyway, because you will be measuring the whole circuit at that moment. So that's one of the tricks which we are using, trying to shorten our circuits. The other thing is, you've seen the deferred measurement principle at the beginning of this presentation, and I used exactly the prescription from the textbook. So rather than small trick here, this is ancilla which just does Control Z on those qubits. If you add another control here, essentially it's Control Z, Control Z over all those qubits. If you add Hadamard operators here, essentially you are negating this qubit, and you could have measured it here, but sorry, I'll be going back to this one. You could have measured this here, but I'm trying to go as prescribed, so I'm using C0 on this wire, trying to not to measure and defer the measurement till the very end. So see what happens. Indeed, the probabilities, as you can see from the amplitudes in the blue box to the right, are not changing that much. So exactly the same. However, I did use additional 3 qubits, which are scarce resource. And what's worse, I needed to add the control. I was honest here. I didn't need to add control to another Control Z, the oracle operator here, because it doesn't change anything. However, I needed to add control to those small diffusion operators here. What's the result? Essentially, you are multiplying the resources needed for that computation. So while in-circuit measurement is, in fact, providing exactly same probabilities of measuring the desired state at the end of the computation, it does so by using much more resources. And this is something which is important if your hardware allows for in-circuit measurements. It is doable in any of the realizations of the current quantum computers. However, on some, it is much harder than on others, because you need the low noise, very fast electronics to be able to read out, and then make sure that there is no crosstalk to other qubits around. That's hard. On the superconducting hardware, it is extremely hard to do. They are hardware manufacturers who are attempting doing this. None did, to my knowledge, nobody actually provided the ability to test that for the external world. If you remember Rigetti computing, they were big proponents of the in-circuit measurements. Their simulator does it, their hardware doesn't. So, well, actually, at least as we can access this remotely. So that's the state of the ability to do in-circuit measurements. However, if you could do them, look what happens. You don't need that many of the additional ancillas. And there is something which I mentioned early on, no cloning, because you cannot copy the state, so you cannot have a spare copy if you want to run your tree-structure computation. Look at the blue boxes with the amplitudes after the first module, or sorry, the second module, and after the third module. Yes, they're exactly the same. So I'm not talking about the efficiency of this particular circuit. You see that each module needs 2 oracle calls. One is setting up the qubit to be measured, and the other one just flips the state. We have some ways of dealing with that, but for now, all I want to show is that essentially we copied the state which is useful for the computation. Can we copy the arbitrary quantum state? Of course not. The Rubiks, Wouters, and others proofs are solid. However, it doesn't mean that you cannot generate the copy, even if the data is originally unstructured, in such a way that this module, starting here, small diffusion operator, flipping oracle, another diffusion operator, another oracle, this time setting the qubit to be measured. That's something which can be done in principle if your hardware allows for the in-circuit measurements. And this module is repeated along the circuit. Look what happens if the quality, or essentially the entanglement between those qubits, so the state across many qubits, defined by on many qubits, degrades with time by the decoherence, most likely exponentially fast. So you might be able to run only few of those modules. Nevertheless, the probability of success in each of them is significant. If you run this circuit, like this module, like 3 times, your expected number of the oracle calls, even taking into account the fact that we are using 2 per module, is something like 3.9, which is pretty close to pi over to 3.9, which is pretty close to essentially pi, which is the result by Grover. So not that far, and we have an ability to measure in circuit, and that's something which shortens the circuit length, minimal circuit length, which you need to run to get anything better than the classical solution. So that's another of the techniques which we did patent, and we intend to run this on the actual hardware as soon as it is available to us. Obviously, each of those measurements, I just use the tool with the limited expression power. Obviously, each of those measurements can result in measuring 1, meaning that this oracle set this bit for the particular state. And what happens then? Then you just measure everything else, because that's your desired state. And it can happen at arbitrary end of the module. This measurement can either yield 0, worst case, you continue, or 1, and then you finish. If you can do this, essentially you build a tree-like structure for this computation, and as long as your hardware allows, you can run that indefinitely, running the same module, waiting till this measurement yields 1, and then having the result here. So this gets more complicated, a bit more complicated if you use more qubits. So you need to do some processing in the case where this measurement yields 1. However, it is still manageable, and you know what kind of the operations you need to run. Please note that this oracle, which is, I guess, all the controls, can be modified, and the result will be the same. In a sense, it will yield the proper result, matching the oracle. So we created, by the computation, by setting this thing here first, we created a structure which we exploit in something which didn't have that structure initially. This tree-like computation is possible only because we set up this structure. You might ask whether it does scale to the bigger number of qubits. If you look at the structure of this, it's using the pretty simple tree to get there. However, if you try hard enough, and that's like 3 versions of the main result of the paper, which we'll be putting up on arXiv shortly. The main result is that you can do that with no penalty. All those tricks are possible using small diffusion operators, which save gates, obviously, and it doesn't add too many of the additional gates with keeping the oracle calls, the number of oracle calls constant. That's how you do this. As you can see, there is now more qubits, and that's the basic circuit, which provides for the recursion. You can build those circuits into bigger ones and then have a formal proof that it does scale properly. So that's something which we are very proud of. And that's the core of the result which we do have ready now. So with that, I'm ready to take the questions. I just fly this slide. That's what we are doing. Essentially, Beit is here to provide solutions on real hardware sooner, saving oracle calls and having idea how to use those savings into providing actual solutions to hard industrial problems when the scale is bigger. We hope that we will be able to do that before you get into the fully error-corrected million qubits quantum computers. With those techniques, you can make that faster, but the first step will be to show that you can reliably find one element out of 16, one marked element out of 16, which so far nobody was able to show using any real quantum hardware. With that, I don't know what was the plan. I'm ready to take the questions if there is a way to do this. If not, thank you very much. Debu?
So there's a question, how does Beit make quantum computation more efficient by algorithmic optimization or compiler tech or a combination of both?
Well, by a combination of both. The stuff we do is something which you've seen, meaning the challenging the assumptions and trying to use the solutions which not many people used before, or in some cases nobody, based on the physics, in a sense that, well, there's nothing wrong with the in-circuit measurements, except that it's hard, right? There's nothing wrong with small diffusion operators, except that there were some theoretical works that you can actually reduce that, but our proven result is stronger. We don't need log scaling factor in the final result, so we are more efficient in that area.
Another question from David Shaw. For NISQ applications, data input is presumably limited. What application for Grover search do you envisage with this limitation?
That's excellent. That's excellent question. Obviously, trying to search the database which you cannot input into your quantum computer is just useless, right? And we had a very long debate about the usefulness we have, but there are formulations where you can get much smaller result. And yeah, I was promising to my guys and to myself that I'll not be going into the details about the future work. Think about the optimization and think about SAT, right? I'm not going to say anything else here. Then the input is smaller. Finding the result is hard, and yes, putting the clauses into on the ancillas into the quantum computer is extremely hard, and it takes a lot of space. But it is less than trying to input the huge database. If you look at the part of our text prepared for the archive, the obvious place where the database word should be was essentially emptied because we don't like the saying that it is the database search. It is not, essentially, because you'll need to input that database into your quantum computer, which is no go. Thanks for that question. Excellent one.
And the other question is, can you please elaborate on the difference between bursting variability algorithm results and yours?
Well, the theoretical, why are you, Helen, why are you laughing all the time? All right, the real difference is the log-log factor. We know how to recursively apply the operators, and we are close to pi/4 times the square root of the number of oracles, and we don't need additional gates. We need just linear to that number, linear number of the additional gates. This is better than the previous results in that area. Wolf was also publishing on this. There was a log-log term in his solution. So slightly better result theoretical.
And the other question from Charlie Lee, how to implement bra product AA in the quantum circuit?
Can you repeat the question? How to implement?
The BRA product AA in the quantum circuit is in the question and answer column in the Q&A section.
Oh.
Or can Charlie ask or not? Can Charlie unmute himself?
Oh, all right. I understand the question now. So essentially, you don't need to do this. This was used in the tool available to me to simulate the measurement. If you do the measurement, then you will have that qubit on which you did the measurement collapsing to either 0 state or 1 state. I simulated that with post-selection after the measurement. We can go either way, and if you want me, I can go back to the circuit doing this. No, you are not implementing that. It's just the result of the measurement. You are happy with either one. You continue if it is 0, meaning you didn't find the result, or you measure all the remaining qubits if you got 1 as a measurement result. The tool had a limitation. If I did the measurement, it wouldn't let me use that qubit anymore. So I needed to do the post-selection on this one. No, we are not implementing that. It's not possible to implement. If you do the post-selection, you have much more powerful computation model.
And the next question is, with your paper from 1997, I did not understand, let me see. I did not understand what you did wrong. What was the lesson learned?
Well, it appeared right to me as well, but it was wrong in the sense that I ignored the fact that if you do measurement, you are essentially moving part of your quantum state into the subspace where it cannot interfere with the remaining part. And it is no go. At that moment, you are not getting the quantum speed up because you cannot amplify the amplitude. So that was the biggest error in that old paper. It took me like 23 years to overcome, right? So yeah, that was the main error there. Just don't go and read that. I was making fun of myself, right? Just, no, it's not worth it. Not worth your time.
And the next question from Dr. Shaw. You mentioned you have patented several of your circuit optimizations. Is that with the EU Patents Office or other? What time horizon are you protected on?
All right, so essentially, yes, this is a loaded question, David. Thanks for this. Loaded because those optimizations are valid for the NISQ era, right? And we are patenting for like 10 years standard time. So our hope is that we will be out of this era before or at that time, right? You can do the extension. About where, we are patenting in the US Patent Office. We did incorporate in the US despite the fact that all the development is in Poland. And if you want to know, and I think it might be interesting for not only for David, but for others, is that, yeah, I was always against patenting. I was always for open source and the sharing. However, if you go to the really big players with really deep war chests in that area, and when they invite you to share and work with them, and then you are the only startup executive in the room asking the question, if we work on that together, our software, your hardware, who owns the IP? And there is a silence, and then there is an answer. We cannot be held hostage to anything which can improve our computers. And at that moment, it is, I'm out of the room, right? We don't have the might and the resources of the huge corporation. The only thing we have is the IP. It affects both hiring, it affects our ability to stand on our feet on the market. So as long as that's the proposal for the collaboration coming from people who have enough money to attract whoever they want and enough money to build the hardware, we will be patenting. I fully understand that this is a ticket to the lottery, essentially, right? You cannot tell whether you'll be able to enforce this, but better to have a ticket to the lottery than absolutely nothing, which we were offered in those conversations. Did I answer your question, David? I can take another one from Walid. I'll be answering live. The paper is not up yet. And again, I'm pretty ashamed. I'll tell you the story. The title is something, I'll need to check this, but they use my name, right? These Voiters and why they are better or something like this. And we have a big paper, which is the mother of all our papers, and we take sections of this and just make that ready for publication. I was busy with preparing circuits for one of our hardware partners, And I didn't pay attention to the theoretical mathematicians who were playing with that. And now changing the name of that paper will be extremely difficult because you'll be screwing up stuff inside. So it might be something about Voiter. That's how, well, there was a play, right? There was a Grover search, and we thought that we have a better search, and we are Beit, so it was Beiter search. And when I was not paying attention, they changed that to Voiter. So yeah, I'll talk to them afterwards, right? But it might be that title sticking. I hope not. And the paper is not up yet. So as you see, the main result has like 3 different formulations. So expect that shortly, but I'm hearing from them that shortly for last 4 weeks or something. So we might need to wait for the final version on the archive and then in publication.
The next question is, which qubit system do you feel will be the most reliable error-free in the future?
Excellent. Excellent question. Who is posing those questions? You know, many years back when the only solution in existence were superconducting qubits, I had that problem with actually driving. I was experimental physicist. I've been building accelerators and detectors and run physics on those things, right? We were pretty warm compared to what those guys need to do on the superconducting qubits. Nevertheless, getting the electronics, signals from your computer at room temperature, whatever the stages you are using, down to millikelvins, is extremely hard. Getting that thing at the very end, essentially emitting microwave radiation and limiting crosstalk at the same time, is extremely hard, right? And so on and so forth. So I don't think that the superconducting qubits will be the basis of the future quantum computers. And we at Beit are trying to stay equal distance from different vendors and the ideas, because we truly believe that's like something in the beginning of 90s or 1900s in the airspace, in the plane industry. There are so many concepts about planes, about cars, how they should look like. Look outside the window, now all they look the same, right? Because there is a design which is proven and working. And what do we have? Photonic computers, topological computers using some defects in some structure. We have the superconducting silicon-based ones. We have a germanium, non-superconducting, using something which was used in the floating gate tunneling transistors before, only at a smaller scale. We have ion traps. Come on, one of those, or maybe a combination of those, will eventually work. Definitely, it's way too early to say which one would win. My personal bet is they will have dramatic scaling problems if you try to scale superconducting computers, which are prevailing right now. For the reason, right? Look at what happened. The Google supremacy experiment was done on Sycamore 54, right? A couple of years back, they said they'll do this on Bristlecone 72. What happened to Bristlecone? It had same topology, it was bigger, and somehow before they claimed the supremacy, they needed to do the step back. Was the 72 qubit machine too hard to control? That's my guess. That's exactly my guess. At the same time, it was like late 2018. There were promises from Google, there were promises from Rigetti about 120, 150 qubit superconducting computers 2 years back. Where are they? So that's my personal bet, and I'm obviously doing the selection bias in assessing the facts, but I'm claiming that for quite some time now, and it looks like they are and around, right? Where are the big superconducting machines? And for our stuff to work, we need something like 200 of the gate depth and something like 200 qubit count, right? So quite away from the moment we are at this moment.
And Emma make a comment. It was because they didn't have tunable cupola on Bristol cone, and they need to avoid crosstalk among nearby qubits.
Did you mention crosstalk, right? So the original design was not having the tunable couplers. Asking that question, I'm pretty sure that you know the answer as well as I do. Like the Chad-Rigetti telling them that you don't need to tune every single one, you need to tune every other one, and it is enough. And all those discussions, because it is hard. Because it is hard. So I might be wrong as anybody. You know, the predictions, especially about the future, are hard. But I see the difficulty in that technology, in scaling this up. Because the more qubits you pack into this thing, the more crosstalk you will have, right? Tunable or not, right? You are entering, if you do the tunable qubits, you're entering something which is known in the telecommunications as the frequency assignment, right? How far can the particular coupler or the frequency of the particular coupler go, right? How many others will be tuned to the same frequency, or how many different frequencies can you use to have all those tunable, right? You are getting into something really, really hard, which was known from managing networks, telecommunication networks, for example, but that's like the pure physics there.
And MRC is from Simon's Institute, taught by Google. It's Emma's comment. Another question is, what is your take on quantum error correction, QEC? Do you see it as a challenge in quantum computer becoming mainstream?
As I said, I think that with some clever techniques, you can do error mitigation before you will be able to do the full error correction. And obviously, if they were fully error corrected quantum computers on the horizon, we at Beit will not be turning our attention to NISQ ones. We think that it will be a couple of years, we'll be living with NISQ machines, getting better gate fidelities, bigger counts, and because of the gate qubit counts, and because of the gate fidelities, we will be getting longer circuits, and we'll need to play with this, right? So error mitigation, I didn't mention this, and thank you for the question. In some of our qubits, you can flip the qubit mid-circuit, and nothing happens at the end. So some rudimentary error mitigation is already built in if you do the computation our way. The other thing is that if you do that modularly, you can actually stop with, if you are successful measuring, before you execute all your circuit. So there will be techniques developed. And however, if your question is, would not fully error-corrected quantum computers be useful in practice? My answer is I don't know. When we tried working with Ocado, the British greengrocer, our best solution using D-Wave at that time was something like the 20 by 20 grid running TSP, parallel TSP there. Our Rigetti solution was about the same size. And our best classical one, those guys are really good at running large problems fast. Our best classical one was a grid 100 by 100. It was less than the actual warehouse they were running. So they were obviously running suboptimally, but we couldn't help them with quantum machines. And getting the parallel TSP on the grid of 100 by 100 and something like 1600 robots on that grid is hard enough, and it will be difficult actually to optimize on the existing machines. So I repeat somebody else, and I think it was John Martinez, that the competing against the classical computers is hard because they are so darn good, and that's my answer. Error correction is a must, or error mitigation in the midterm, but how far it can go, I'm old enough to remember where the memory banks used 9 bits. One was parity check, because people were assuming that the memory will be flipping bits, and you could check whether it happened by the parity bit. So I think that we are in a very similar stage with quantum computers. However, very clearly, the problem is manifold harder.
Reflecting on the experience, the short depth circuit that worked well in the simulator but took longer in the hardware, is it understood why or what makes it take longer?
Yes, of course, and we didn't touch on that in that talk. Essentially, there are 3 things. One is the directional gates. The other thing is that for some reason they try to spread the computation across all the qubits available. So we are running circuit which needed like 6 qubits on the machine which had 15 of those. And the transpiler tried to balance the load. Very clearly it was happening. But it adds swaps. And even that circuit which I displayed was shorter, significantly shorter than the circuits which were run back in 2018. After transpiling, it used something like 104 2-qubit gates. And it is too much for the machine, as opposed to something like 800 2-qubit gates, which was the best result before. So even 104 gates as executed, right? It's not at that level, it's after transpiling. Even that was too much for the reliable running. So their circuits get actually expanded if you transpile them, because they need to take into account the limitations of the hardware, not to mention the topology and connectivity of the qubit. Yet another thing which is crucial. But again, if you remember the first slide of this presentation, I think that trying to go with the full connectivity of each qubit goes against physics, and we'll be seeing that rising its ugly head from some other place if you try to push the connectivity too far. So that's just a guess.
And there's another question from Emma. Why the choice to work on the Grovers for NISQ rather than variational algorithms?
Where is it?
Why
the choice to work on Grovers for NISQ rather than, well, come on. If nobody can run this, I can assure you that I can run any variational algorithm on the class, emulating that on the classical machine easily, right? Even the chemistry done so far by people running this, I can do that easily on the classical machine, just because of those gate depths and the circuit depths and the hybrid model. It's easy, right? I don't see a point in running the variational algorithms, phase estimation and stuff like this on the actual hardware, because I can emulate that perfectly, right? If I can run something which is Grover-like, then I have a measure how much better I am from the classical machine. It's not claiming the quantum advantage, because I can simulate those circuits. And we had that discussion with people from IBM several times, right? Nevertheless, the number of oracle calls is a good measure. It means that I do have the entanglement inside, which helps in getting this machine running better than the classical one. And that's the reason. I don't want to say that in current state, on the actual hardware, variational algorithms are useless. But think about this. If they cannot run Grover on picking one element out of 16, what can they do with variational algorithm? So that was the motivation. We want to do that better. And actually, if you can do this, then you can go back to actually improving your techniques in variational algorithms. We've been studying them, obviously, but that's the main motivation. Let's do something on the real hardware, which has not been done before.
Another question from Peter. Do you intend to tackle any problems in chemistry or material science?
I said I will not be saying about the future, but I can address this one, right? So there are people hoping that if you get to something like 50, 60 qubits, you'll be able to handle reasonable chemistry, because that's about the number of electrons of the outer shells of the reagents there, right? That's how people think about this. It's utterly not true. In order to run the chemistry, you're essentially taking the classical approximation to solving Schrödinger equation of multi-electron Schrödinger equation and get either variational or perturbative methods, or mix both. And that's how you do those computations. So going the full circuit, so you have the quantum system, you model that classically, then you do the approximations to the classical equations so they are simpler, and then you feed it back to the quantum system. It doesn't look like a solution for me. So for that to work, and you can see the scaling of those, right? You are getting something like the number of the outer shell electrons or orbitals to the power of 9. Come on, well, you can solve the hydrogen. My students 20 years back were solving the chemistry of the hydrogen with no quantum computers whatsoever, right? With the mainframes, which were weaker than we have our smartphones, right? So no, not anytime soon. Start with something which is simple. Grover search, very well defined. You know what to expect. You can measure. I'm an experimental physicist, right? I really hate that when I see the graphs with no error bars on them, right? Come on, guys, it's not the result, right? It's just guessing, more or less. So yeah, I don't see us tackling any chemistry, except that we might be able to have the optimization methods better than other people because of the particular approach to solving those problems via Oracle. Let me sketch one of the algorithms which we are not using. That's why I'm keeping my word of not saying the future problems. I mentioned that to some people, and I've seen that then done by others. So imagine that you are doing the Grover search, and your Oracle tags a certain value above the ground state energy, right? If it is big enough, you do have many potential solutions. So your algorithm will be fast. If you do it our way, it will be even faster, but you can count on something like the square root of the number of solutions over the size of the space you are searching. The moment you found this solution, you do the partial measurement, so you don't collapse the whole state. You change the Oracle to find half of what you had so far and go to the ground state that way. Would that work using just the Oracle kind of computation? I would think yes, you can do this. You need bigger circuits because you need to keep that state after the partial measurement. Is it a viable optimization method? I do think yes. Can we run this? No, we cannot run a single simple Grover on 4 qubits, right? So it will take time, we'll get there. And yes, you might be able to tackle some of those computations in the novel way, given the power which the quantum computing paradigm provides.
The next question is the phase oracle better than the Boolean oracle?
Equal, doesn't matter. You can convert one to the other easily, right? By using Hadamard operators around the target qubit, or not even target qubit. If you do the, well, all right, okay. I'll change my answer. Yes, the phase oracle is better. And the reason is that it doesn't need additional qubit. You can do the phase oracle into the already marked circuit. If you remember the slides, if you use 4 qubits, I can do control Z, which is symmetric, and I don't need any oracle. If you have a Boolean oracle, you need additional qubit. And then if you have that additional ancilla qubit, you can do exactly the same which you can do with the phase oracle. Do you have slides to share? I was not able to join. Yes, I can make the slides available via Helen, but I guess it was recorded, so I hope you will be able to get the recording with the slides.
Next question is, a search in a large data set requires access to the data bank. One is searching in. How would that be done in a quantum computer?
I think this is that question was asked, was posed before, right? How you input the data if you search. I don't need to input. Obviously, if I do input, I know what the data I'm inputting, so I'll be linearly. This will take time linear in the size of the database, and I will have in my hand the marked oracle. So rather than inputting, if I have something which scales like n, I can as well run the classical algorithm finding the marked element, right? So it is not the database. That's why from our theoretical paper, the word database was dropped out. We don't have a good substitute. We prefer to say it's unstructured search. Imagine SAT, right? It will be compact in the description. It will be extremely hard, but still, it will be clauses which do not scale exponentially. And how much can you improve SAT is a excellent question and a field of study for us at least.
And I have a question: how many qubits can we add in the in-circuit improvement? How many more qubits? I mean, you can add. But I see three. I see you have 3 qubits in the in-circuit improvement in your slides.
Well, there might be some. It was. You cannot add as many as you want, but you'll be out of the comparison with the original Grover search if you extend that, right? Every module there adds 2 oracle calls. Again, not a word more about this, how you can trick this thingy, but as it stands, you need to use 2 oracle calls per each module. And the probabilities, which here was pretty high, for 4 qubits are pretty high, drop if you go to the higher number of qubits. Nevertheless, you can run those modules and the growth is not that bad. So essentially, you'll need to do that anyway, because you'll need those ancillas to calculate your control Z's if they need to reach the whole space, because otherwise you cannot do this, right? It's one way or another. You'll be limited by the number of qubits you can add, or you'll be limited by the circuit length if you do the expansion in place without using ancillas. It is hard. It's this bloody Rubik cube which you try to set in the blindly, essentially, all taped over. You cannot see colors. So yes, it's a trade-off.
The previous person asked you a search in a large data set require access to data bank when it's searching in. And he asked the same question. How do you know what are you searching for then?
No, I fully understand where it comes from, right? This is like, if the oracle is just the control Z to create that oracle, I needed to know. But if you do other problems, it's not the case. It's just the model, right? And I know that even if I go to 0 with additional qubits, I'll still be having that number of oracles and that number of the control Z operators. So this is a theoretical work, and with 2 aims. One, run something nobody was able to run on the hardware despite the successful runs on the simulation. And the other one, use this technique of the, perhaps more than I do about the query complexity. Scott Aronson's work and his PhD's work on that, and the recent result by Microsoft. And yes, there are limitations to that model, but it is a valid model. So I'm not assuming that I'm solving any real problem searching the database. I'm avoiding this, even saying the database here.
And another question from Dr. Franks. If you were 25 years old again today, seeing what we can see about the industry presently, would you invest your intellectual life on quantum computing? Would you make a career bet on it?
Yes, I did make my career bet, right? I did work in something else. I was so happy that I could return to that. The problem was that when I started back in 1993, I guess that was, this was just the theoretical curiosity, right? There was no quantum computers on the horizon. This was a time where Feynman, it was like 3 years or 4 years after his death, right? So he was saying those things. It is a different paradigm. And intellectually, it's extremely challenging. And at the same time, it's extremely rewarding seeing that it's happening right now, right? Even if the systems are small. I can tell you how it looked when I was physicist doing the accelerator physics. How many dot runs we had of the ZEOS accelerator and how happy we were when it started working for the first time. That's rewarding. So yes, the answer is definitely yes, because it's like 23 years less than I spent on this, right?
Another question from Emma again. Advice for those recently being inspired to learn quantum computing. Take the time for a PhD or that take route and get on PhD role at the quantum computing company.
Excellent question again. And I can say from the experience of building the team at Beit, as I bragged already, right? We're placing extremely highly, or our engineers were placing extremely highly in the IBM Quantum Challenge, right? They were professionals participating, and those guys aced the solution. Actually, the small bug stopped them from finding the optimal 45 decomposition. And many of them are not pursuing PhD. And many of them are actually, we do have dropouts. It's like Google in the old days. When I was the engineering director for Google, we had this statement that if you're going after your PhD, we are not accepting you to Google until you finish, because we had way too many all by thesis people who started and dropped out because work at Google was so interesting. And guilty as charged, we see that at Beit at that moment. We do have people who dropped out of the university. At the same time, you know, they are publishing, and the influence of what we are doing is much, much higher if they graduate or even postdoc in the bigger team. So I don't see, especially what's happening with the pandemics, right? What would be the diploma worth? What would be a PhD worth? You'll not be working on campus, right? You'll be working remotely. So getting your hands on something which is real and working with the top minds in the whole world, hardware guys, software guys, having partnerships with them, gets you much further than you could get, at least in Polish universities at that moment. It might be different in the US, I don't know. I don't know enough about the universities in the US, but it will be a challenging time for academia as we know it, right? So I would, if you had an opportunity to work with a team which does quantum computing, if I were you, I'll do this. Yeah, I think I learned much more in the last several years in the discussions with people who are not in the field than from my studies of physics. Yeah, I do have intuitions, and that's the reason why some of those algorithms are stemming from something which I thought about. But equally well, I could be wrong, and my mathematicians in the team just straighten me up, and that's how it works.
The next question from David. Will the quantum phase estimation for quantum chemistry require less gates than Grover search algorithm? I mean, the oracles can require many gates, so will the decrease the practicality of Grover for the NISQ era, like QPE has small practicality?
Well, it's again, there might be some clever techniques reducing the number of gates if you do some shortcuts in the QPE. And as it is run now, essentially you optimize for the number of gates you can run actually on your hardware, right? So that's how you do. Then you go to the classical part, you modify, and then you rerun with the new setting parameters. But I don't believe that being limited to something like 10, 20 of the circuit depth, you can actually go beyond something which you could get simulating the quantum circuit. So frankly, the answer is that neither QPE nor Grover are practical at that stage. But getting to understand those algorithms and knowing how they will scale is something which is worth working on, because there would be a moment where if you do that cleverly, you'll be able to actually run those calculations. I'm not saying it will be QPE or Grover and the Oracle based computation, but without knowing those tricks, you are limited to the textbook circuits, which everybody seems to be so fond of, but they're getting you nowhere. Using those tricks, you will be much, much faster because your circuits are like 8-fold shorter than the textbook ones, meaning you'll be able to run them on the smaller machines and sooner.
The next question is, can we apply a noisy model to the Grover algorithm, and how? Can we apply a noise model to the Grover algorithm, and how?
Oh, yeah. We did that. I decided to shorten the presentation and don't show this. Essentially, there are several theoretical publications, and we did some experiments in practice. So you have all the phase and bit flip errors you can think, and you can model them into the circuit. You can also have the decoherence. You can have bias. So there is like in physics, right? The better you understand your equipment, the better you can correct for systematics, right? IBM draws everything to 0, 0, 0, 0 state. That's the decay. And you can model that. You can see how it changes along extending the length of your calculation. And that's how you build this model. And then knowing the model, you can correct on this bias. And the other thing is something which is random and also destroying the thing. And this is also modeled, right? Those are T0, T1 times. Those are infidelities of gates. And this is doable, actually. So if you work in Qiskit, then you can include the noise model, and it'll give you something which is different from the theoretically run circuit.
So far, I don't have more questions.
All right.
Okay, can you take over? Is that all?
Okay, thank you very much.
Thank you very much for coming.
Yeah.
I hope you'll come back with the better search when you find, much better search, and we'll have another session. And so let me go through some of the announcements I did before.
All right. So thanks again. And yeah, thank you for having me. And I'll be happy to come again, either in person if we are allowed to, or again remotely if we have new results. Thanks again.
Okay, so we have few announcements. we are with Association Quantum. So go to the website there. We have announcements on Thursday, May 27. Check it out. Then we have May 21st. Dr. Terrell French will do a tutorial. And on June 9th, Quantum Ecosystem, the two through the Quantum Ecosystem by Doug Finke. Okay.